So we'll go ahead and get started, continuing on looking at this invisible thing we call thermal energy and heat and enthalpy and thermodynamic problems. So today, this is the last part we have for this unit because, yep, we did go back and pick up chemical reactions. So we're going to get halfway through it today, and then Wednesday we'll finish up, and then Friday we're on to unit 4 material. Wow. So there's a lot of things in chemistry that I think it really should have a rap song made after it, and this is one of them, where it takes energy to break bonds, and when bonds are formed, energy is released. So you need to, and there are different types of bonds. I want to focus on what's called intermolecular bonds. So in order to understand intermolecular bonds, I'm going to go ahead and hopefully animate this again. Intermolecular bonds are the things that connect molecules. So for instance, those water molecules water's in this liquid state, and the water molecule, we have intermolecular bond connecting them. Now when it's a solid, there's a network of intermolecular bonds. So a high degree of bonding. When it's a liquid, some of those bonds are broken. When it's a gas, there are no intermolecular bonds. So let's see if it works. Yeah, this is the one that I tried to loop, and it doesn't loop very well. One more time. Watch fast. So all matter is in motion. You saw a little bit of that motion. Gases have the most amount of motion. Solids have the least amount of motion. And kind of related to that motion is the degree of intermolecular bonds. So it takes energy to break bonds. And when bonds are formed, energy is released. It's probably easiest to kind of think as matter going from a solid to a liquid and matter going from a liquid to a gas. To me, that's pretty, I can see that. I'm breaking chemical bonds. Okay, if you want to melt an ice cube, you add heat. If you want to have water go from its liquid state now to its gaseous state, you add heat. Okay? We said that when you add heat to something, that's an endothermic process. So I might even go ahead and draw this up here so I can refer to it later. These 3 physical phases, solid, liquid, and gas. When we go from left to right, we are breaking bonds. Energy is put in, we're going to call that endothermic, means energy is put in. Energy is in, energy is added. Well, from right back to left again may not be as intuitive. When gas particles slow down to the point intermolecular bonds can form, so it forms its liquid state, bonds are formed, energy is released. When molecules slow down enough so intermolecular bonds are formed, so it goes from a liquid to a solid, energy is released. Okay, so I could go ahead and draw a line from right back to left again, and I would say forming bonds, and I would put exothermic, and I would put E released. I'm going to go ahead and change this. Instead of E in, I'm going to put E energy absorbed. How's that? Cool. All right. So that's the sort of thing we can talk about in thermodynamics. So this is kind of a review of some things that I think we've talked about. All matters in motion. When it's in a solid state, it has least amount of motion, least amount of kinetic energy. When it's gaseous state, it has the most amount of motion, most kinetic energy. So hopefully it kind of makes sense. Not only are we changing phases as we go from solid to a liquid and a liquid to a gas, okay? But we're endothermic, we're adding energy, then the particles are going faster. Okay, exothermic, we're taking energy out, and particles are going slower. So we talked about this before, kind of related to the fact of how matter is behaving in its solid state. It's a high degree of intermolecular bonding, low kinetic energy, so it has a definite size. It doesn't take on the size nor the shape of its container. Liquids will take on the shape of their container, but has a definite size. Medium with regard to intermolecular bonding and kinetic energy. Gases are my favorite. In Unit 5 and here we're going to talk more about gases. Gases take on the shape and the volume of their container. They basically have no intermolecular bonds, and they have a high degree, the highest degree of motion, so kinetic energy. So if I were to ask you, and I think I'm going to go ahead and put these little words up here, hopefully you would tell me when something goes from a solid to a liquid, that's melting. High-tech term, right? Melt. Melting. When something goes from a liquid to a gas, what would you call that? I would call it evaporation or vaporization. Vaporization. So as I've drawn these, hopefully we're all on the same page. I would call these endothermic processes. Endothermic. I'll put EN for endo. Well, let's take a look at some other phase changes. When something goes from a liquid to a solid, hopefully you would tell me that's freezing. So from a liquid to a solid, that's freezing. And that's actually, energy is going to be released when that happens. We're going to work some problems and we're going to actually quantify that energy that's released. So I'm going to put XO. So it's going to have what? A negative delta H. And then last but not least, we have this one. When something goes from a gas to a liquid, we call that condensation. Or condensing. And that's also going to be exothermic. Energy is going to be released. So I have a couple of videos to run past you. And again, it's kind of a busy slide here on the board, but we talk about phase changes, physical phase changes. The ones that break bonds are the melting and vaporization. Sublimation when it's going from a solid to a gas. By the way, sometimes some people use sublimation to both talk about going from a solid to a gas and a gas to a solid, but I prefer deposition. So the exothermic phase changes when bonds are being formed would be from what I call right back to left again. So that would be your condensation and your freezing and your deposition. So it takes energy to break bonds, and when bonds are formed, energy is released. All of these energies, whether they're released or absorbed, are called latent heats. Latent heats. Anytime you see latent heat, think energy and think phase change. So what we do, well, in addition to calling them latent heats, is we kind of bring in this enthalpy of vaporization. Heat of vaporization, same thing. So heat of vaporization, enthalpy of vaporization, latent heat of vaporization, you're like, are you serious? Could you call it anything else? Well, let's kind of focus on what it's talking about. It's talking about this right here. What does vaporization mean? It's going from a liquid to a gas. We all know that. That's vaporization. Endothermic, you bet. So what we do is we use actually a delta H, the change in enthalpy associated with subscript vaporization. It is a latent heat because we're talking about the energy required for something to go transition from a liquid to a gas. That's what vaporization means. These latent heats, these enthalpies of vaporization will be given in energy per amount. So it's energy per either mole of substance that is vaporizing or energy per gram of substance that's vaporizing. Energy units could be kilojoules or joules. So the title of this slide says heat of condensation. So let's kind of get our bearings here. Previous slide was heat of vaporization. This slide is heat of condensation. If you're like, you know what? I bet the same amount of energy is required to go from a liquid to a gas is as released as that same material goes, energy is released as that material goes from a gas to a liquid. And you are totally right. You are spot on. Those are both latent heats. Latent heat of vaporization, latent heat of condensation. So we'll make this a delta H, change in enthalpy associated with the phase change of condensation, which is, you guys knew this before you came into this class, condensation is matter going from its gaseous to its liquid state. The relationship for the same material between those two things, they are equal in magnitude, but they are opposite in sign. That's kind of what's being shown here. Their absolute values are the same. We could say that the enthalpy of condensation is equal to negative change in enthalpy associated with vaporization. Makes sense. Totally. So the deal is when we go to look at thermodynamic properties of material, you will definitely see these endothermic ones, okay, but you won't see the exothermic ones. So you're going to see the heat of vaporization, but you won't see the heat of condensation. If you need it, you change the sign. Let's talk about the other main phase change, skipping sublimation. Now, for whatever reason, I think if I'm melting up there, I'm going to go ahead next to my melting, I'm going to put fusion. It means the same thing. So this heat of fusion, or change in enthalpy of fusion, is the same thing as the heat of melting. What does melting mean? It means going from a solid to a liquid. Is it endothermic? Yep, you bet. Is it going to show up in the tables? Yep, you bet. So the opposite of melting would be freezing. So here we go. So the heat of fusion is the same thing as the latent heat of melting. So yep, endothermic, the opposite of endothermic, the exothermic process that's related to melting would be freezing. So again, we have this equal in magnitude but opposite in sign thing going on. Again, you will see the heat of fusion, but you won't see the heat of freezing. If you need to know how much energy is liberated during the freezing process, you grab the heat of fusion and slap a negative sign on it. So you just kind of got to, I'm a visual person, so I just got to kind of picture these things. Okay. So I did not bring my calculator, so I meant to. What I want to do, because I don't do it until later, is just to pick one of these and do a problem. Before I pick one of these and do a problem, let's see what we got. So we have elements, compounds. Now, these are phase change temperatures. The temperature at which, in this case, let's see, let's put it up on the diagram, melting point temperature. So what do you think? Right here. Well, I'll just put it right here. I'll put T sub MP, melting point temperature. We care at what temperature that happens, and you'll kind of see why when we work problems. For the enthalpies of vaporization In that column, I have the boiling point temperatures. There are times when you're working problems, in order to have it make sense, you're going to need to know the temperature at which that stuff boils. So what I started to say is, I'm going to butcher this. We're going to be dealing with ice here in a minute. So let's go ahead and find water. And I'm going to go ahead and draw, these are my ice cubes. So this is H2O solid. I'm going to melt it. And I'm going to go ahead and I'll tell you why this is going to happen. I'm going to have it, the whole thing happen at 0 degrees Celsius. That's not a reaction condition, that's just the temperature which is happening. And let's say, let's go, this shouldn't be too bad. I'm going to go with 100 grams of water, solid, and I want it to go ahead and I'll have it in one of my famous beakers, and I want to melt it. I'll still have 100 grams, obviously. Now it will be liquid water. So the way this works is, I think I have a little formula coming up. Q is change in thermal energy. I'm going to say the Q associated with melting equals the mass and then times the delta H sub fusion, which is melt. Let me show you, let's not make it harder than it is. So in this problem, all it would be is my 100 grams. And then notice that I have two choices. For water, I can go with either energy per gram, which I'm going to, or energy per mole. I'm going to go with energy per gram. So that 338 is units of joules per gram. So the thermal energy required to accomplish this process right at the freezing and melting point temperature is it, oh yeah, so it's times 100, right? I can do that, 33800. Units, joules, and I need 3 sig figs, and I'm showing 3 sig figs as long as I don't put a decimal there. That number looks pretty ugly. You know why? Because we're used to going ahead and converting it to kilojoules. So let me go ahead and 33800 joules, 1 kilojoule per 1,000 joules. And I got 33.8 kilojoules. I feel good about that. That's how it works. And if we were freezing instead of melting, that would be the amount of energy released. And it would be negative. All right, very good. Well, I feel better. So we're going to work this problem, and I'll go ahead and it's several slides for one problem. This is, I think, after we work this problem, it's kind of a good break. It's several slides. We're going to see an energy diagram in a minute, and if it's okay with you, I kind of want to start building on it over here. And I'll show it to you in the slides in a minute. Along the y-axis, I'm going to make temperature, and along the x-axis, I'm going to make energy. So it looks like this. Calculate the total energy needed to convert 500 grams of water in its solid state at negative 50 Celsius to water in its gaseous state at a higher temperature of 200 degrees Celsius. So it looks something like this. My first temperature is a negative 50 Celsius. Let's What temperature does water transition from a solid to liquid? Celsius temperature scale. 0. Yep. The freezing point, melting point temperature of water is 0 degrees Celsius. So here we have negative 50 degrees Celsius. I'm going to go ahead and slap a 0 degrees Celsius, the transition temperature. So I'm going to take water in its solid state and I'm going to ramp it up to water. So this is solid, 500 grams of H2O solid. And I'm going to add energy. And the first bit of energy is still going to be a solid, and it's going to ramp up right to the melting point temperature. Once it reaches the melting point temperature, I'm going to put all my energy into taking that stuff and transitioning it from a solid to a liquid. And to show that step, it's actually going to stay at the same temperature. It's going to hold that 0 degrees Celsius, even though I'm pumping energy into it. All my energy is to go ahead and make it into its liquid state. And at its liquid state, I'm going to go ahead and I'm not going to change its phase until I heat it up to, do you guys know what temperature it boils at? 100 degrees Celsius. So I'm going to keep it a liquid and I'm going to jack up, I'm going to pump it, I'm going to add energy, add energy, add energy. It's going to stay a liquid until it gets to its boiling point temperature. And at that point, I'm ready to go ahead and transition those 500 grams from a liquid to a gas. And it's going to plateau out again at the temperature of boiling. Well, this said I'm going to go beyond my 100 Celsius to 200 Celsius. So here it's in its gaseous state. Finally, I got it all transitioned from a liquid to a gas. And now I'm going to take the gas and I'm going to pump it full of more energy, and it's going to take my gas up to a temperature, and it would keep going, but I get to stop when I get at, I know this isn't drawing scale, but I get to stop when I'm at 200 degrees Celsius. So those are kind of the stepwise things going on. Here we call this is step 1, 2, 3, 4, and step 5. Literally. One of the things we've been talking about is if you can describe an overall process in a series of steps, we said you can add them together, Hess's law. It's exactly what we're going to do here. So, without further ado, step 1. We're going to determine the energy needed to raise the temperature of the solid from negative 50 to its melting point temperature. Step 2. We're going to determine the energy needed to go ahead and take that solid, go to a liquid. This is my melting. Step 2. Step 3, now it's in its liquid state. We're going to go ahead, this should be down right here. We're going to see how much energy it will take to go ahead and change the temperature, that 100 degrees Celsius, its liquid state, from its melting point temperature to its boiling point temperature. Step 4, now it's all a liquid at the boiling point temperature. We're going to go ahead and vaporize it. Step 5 now is we're at the boiling point temperature. We're going to go ahead and take the gas, that the liquid now is all a gas. We're going to go ahead and jack up the temperature of the gas up to 200. So you can't see it very well. This actually is trying to kind of talk you through a little bit. It's a little abbreviated than this. Temperature, the masses are different. the mass of the ice that's given. But notice we have solid water at negative 12 degrees Celsius. Of course, it's negative 50, but negative 12. And you can't see the figures. I cannot read the temperatures there. But according to the caption, if we were to see the temperature for B, now that solid is not negative 12. That solid has been brought up to the melting point temperature. Notice that 30 minutes later, we're holding this same temperature. Okay? Because what's going on is now the heat is being added to go ahead and transition. I don't know if you can see, but there are ice cubes here. Then finally, as you might imagine, after it's all transitioned from a solid to a liquid, then the heat, actually it's coming from the outside room, then the heat actually can go ahead and start raising the temperature of that liquid, and that's what's done here. So we end up with about room temperature water. So anyway, that's how that works. So let's work this particular problem. Again, there are 5 Qs. Now, you could go with Q1, Q2, Q3, Q4, Q5. What are the Qs? Change in thermal energy. Or probably better, you could be more descriptive. The first Q is raising the temperature of the ice. The second Q is melting the ice, etc. Let's see, is this where I want to go back and forth? I practiced this. So here's a figure you have in your slides. Again, this curve is very similar, or whatever, to this curve. Let me take you to the first step, the first Q. So the first Q, we are taking solid water and raising its temperature from negative 50 to 0. We're going to use Q is equal to MC sub P delta T. Totally. Don't let this throw you off, though. The specific heat I had you memorize for liquid water is 4.184 joules per gram degree Celsius. That is not the specific heat of solid ice. Specific heat of water in its solid state is different, 2.06 joules per gram degree Celsius. Mass was given. Of course, our delta T is this difference right here. Okay, it's always final minus initial, so so it'd be 0 minus a negative 50, which is 50. So this way so it's all about plugging and chugging, but you have to bring the units along. And if you bring the units along, it looks like this. So this first Q, we take the mass, 500 decimal grams of water, times the specific heat of water in its solid state, 2.06 joules per gram degree Celsius, times the delta T, which is 50 degrees Celsius. Units cancel, and I can't remember, I think I slap on a joule to kilojoule term. So let's go ahead and slap on 1 kilojoule over 1,000 joules. Give ourselves 3 sig figs. So our Q1 is 51.5 kilojoules. So Q2 then is to go ahead, and now it's in its solid state. We're going to keep it at the same temperature, the transition temperature between solid and liquid, and we're going to go ahead and melt it. So to do this, calculation step 2 looks like this. And by the way, this is kind of what I did aside over here. Simply to find the Q2, all we got to do is take the mass, which is 500 grams, look up on the table what the latent heat of fusion or melting is. It's funny. So it looks like this. 500 3 sig figs grams over 1 times, and didn't I use a different number? Wasn't it 338? This is 333. So this would be your latent heat of fusion or melting, 333 joules over 1 gram. Let's go ahead and get all the way to kilojoules, 1 kilojoule over 1,000 grams, 3 sig figs. So our Q2 is 167 kilojoules. This actually brings up a good point that as you're working the problems, I know some of you had mentioned, you are like, the constant I get is different than, I find different constants than you might find. That's okay. They should be ballpark similar. On a test, I will give you that. If you need it, you probably will. Okay, back to the graph. So now we're ready to take the liquid at 0 degrees Celsius, keep it a liquid, and go to the temperature at which it will transition from a liquid to a gas, which is its boiling point temperature. So Q3 looks like this. Where we're going to use Q is equal to MC sub P delta T. And how do you know which one you're using? Well, it's staying in its liquid state at that point. So the only thing we have going on is raising a certain mass up to from an initial temperature to a final temperature. So this is where you use the specific heat of liquid water is 4.184 joules per gram degree Celsius. So it looks like this. Q3, your mass still is 500 grams, 3 sig figs, times the specific heat of water, 4.184 joules per gram degree Celsius. The delta T is final minus initial. The final is 100, the initial is 0, so you have a delta T of 100 degrees Celsius. And we'll go ahead and introduce a term to get it from joules to kilojoules. 1 kilojoule over 1,000 joules. Round again to 3 significant figures. And we get this third Q as 209 kilojoules. 209. Oh my gosh. Yep. So now it's like a story. Now in the story, it's liquid right at the boiling point temperature, right at the cusp of transitioning from a liquid to a gas, and we're going to go ahead and put all the energy we have now into vaporizing it. Notice that actually the length of this, you can see that the heat of vaporizations are relatively high compared to the heat of fusions. So in this case, we're going to go back and use that M. The Q4 is equal to M times the heat of vaporization. And it looks like this. So we look it up for water, and the heat of vaporization for water is 2.26 times 10 to the third joules per gram. So it would look like this. Q4 is equal to the mass, 500 decimal, 3 sig figs, 500 grams of liquid water converting to gas, times the heat of vaporization, 2.26 times 10 to the third joules per gram. Let's go ahead and convert from joules to kilojoules, 1 kilojoule over 1,000 grams. 3 sig figs, and we get our Q4 as 1.13 times 10 to the third kilojoules. Yep, that was a big one. Oh my goodness gracious. So we're ready for our Q5. So now we have water in its gaseous state over here. Now all we're going to do is jack up the temperature of that gaseous water. And there will be another specific heat associated with water in its gaseous state. So we're going to use Q is equal to MC sub P delta T. The mass is the same. The specific heat of water in its vapor state is 2.06 joules per gram degree Celsius. The delta T, it's always final minus initial, so it's going to be that 200 minus 100. Oh, thank you. I was like, whoa, that 2.06 sounded familiar too. Let's try this one. Okay. Okay, it's close to 2.06. 2.03 joules per gram degree Celsius, thanks. The delta T, that didn't make sense either. It's final minus initial, so it's 200 minus 100 for a delta T of 100 degrees Celsius. So when we plug into Q is equal to MC sub P delta T, it looks like this. So Q5 is the mass, which is 500 grams of water, 3 sig figs, times the specific heat of water in its vapor phase, 2.03 joules per gram degree Celsius, times our delta T, which is 100 degrees Celsius. Tack on converting it to kilojoules from joules, 1 kilojoule over 1,000 joules. Rounding to 3 sig figs. We get our Q5 is 102 kilojoules. Phew. So then all we got to do is add Q1 plus Q2 plus Q3 plus Q4 plus Q5. So Q1 was 51.5 kilojoules, Q2 167 kilojoules, Q3 209 kilojoules, Q4 was the highest, 1,130 kilojoules, and then Q5 is 102 kilojoules. So since we're adding, we round according to fewest decimals, or in this case, tens places. So to me, the fewest tens place I have is actually in the, it's going to be in the tens of kilojoules. Let's see if I rounded it that way. Yeah, I did round it that way. So if you take this number and unpack it, you get 1660 kilojoules, which is rounding to the nearest tens kilojoules. So there you go. Hess's law. Something that taking solid in -50 and converting it through a liquid to a gas and raising it to end up with a gas at 200 degrees Celsius. That's the amount of energy that would be required. Okay? That's as far as I wanted to get. And so we'll pick up with that second problem on Wednesday.